Hey y'all, welcome back. Well, today we're going to have our third and final day of learning about the polar system. I know this has been kind of a quick unit, but really I just wanted to give you a little taste so that if you're going on to Calculus BC next year, that it won't be completely new to you. So today, so far we've already talked about coordinates and equations and a little bit touched on graphing a little bit. Today we're going to look at some sort of miscellaneous polar problems. So given what we already know, what kinds of problems can we solve when functions are given in polar form? So we're going to look at how to find, for instance, the intersection of two polar graphs. We're going to look at how to find like one coordinate given another coordinate. And just answer a few sort of miscellaneous polar questions. So it's not going to be too many, but they do require a little bit of upfront work. So let's jump right into it. Here what we're doing is we are trying to find points of intersection between two curves. So we've got two polar functions, and we want to know where did they intersect. And in problem 3, we're interested in the polar coordinate where they intersect, which is actually be a little easier. And then in number 4, we're looking for the rectangular point where they intersect. So that'll require a little bit more work because essentially what we'll do is we'll find the r comma theta for this one, kind of like we'll do in number 3, and then we'll convert it. So we'll do the r cosine theta, r sine theta stuff. So I'll show you how that plays out. But let's start with number 3. We want to find a coordinate where the two curves intersect. Now this is going to be pretty similar to something that you would or may have solved in Algebra 1 where you solve a system of equations. It's the same kind of idea where you want to isolate both equations for a single variable, and notice here r is isolated in both equations. And what you do is you're going to set the two equations equal to each other and then solve for theta, and then plug theta back in to solve for r. So we're going to use the substitution technique that you learned in Algebra 1 for solving a system of rectangular equations, and you do essentially the same thing here. So when I set these two equal to each other, I'm going to get 12 times theta squared equals, get out of the way there, 5 theta squared plus 2. And so I want to solve this for theta. And then what I'll do is plug it back into theta and see what I get for r. So let's go ahead and plug that in, or not plug it in, let's solve this. I need to subtract 5 theta squared from both sides, which will give me 7 theta squared equals 2. You know what? Let's just run with it. So 7 theta squared equals 2. You know what? I am going to change this. I'm actually going to change this problem here. I'm going to make this a little harder just because I want it to be a little more similar to what you're going to see like on the practice problems and the quiz and stuff. I'm going to make this just 5 theta plus 2. Okay, now I know that's going to kind of change how we work this out. So let's kind of start over here. So delete this squared. So I apologize for that, but here we go. So that means we need to move everything to one side, and we're going to get 12 theta squared minus 5 theta minus 2 equals 0. And this is going to turn into a quadratic, which I know is not really what you wanted to see, but I just think it'd be worth just going through this factoring steps to try to solve this, just to have a little bit of more factoring practice here. So we do have to factor this. I'm going to go ahead and try to come up with two numbers that multiply to give me negative 24. Oh, that's kind of big. I don't need it that big. Two numbers that multiply to give me negative 24, but add up to negative 5. So we want to multiply to give me negative 24, not 27, 24, which is going to be like the negative 2 times 12, and add up to negative 5. So those two values are going to be negative 8 and 3. Again, don't feel too bad if that doesn't come like immediately. It does take a little bit of practice coming up with those two special numbers. And so once we come up with those two numbers, we are going to split up this middle term. The rest of the equation will stay the same. And so we should get, come on, there we go, 12 theta squared minus 8 theta plus 3 theta minus 2 equals 0. We're using the grouping technique here, just in case you're curious what this is called. If you ever want to like Google grouping method, or just look at, really if you go check out my Algebra 1 videos, I go over this in great detail. So just, kind of Google factoring by grouping and you can see my explanation on that one. So we want to group the first two terms and the last two terms. So I'm going to put this little group in parentheses, and I'm going to bring the other group in parentheses, and we're going to factor out the GCF out of each group. So the GCF out of the first group is going to be 4 theta, and I'll get 3 theta minus 2. And then I don't really have a GCF in the second one other than 1, so I'm just going to factor out a 1 and leave the 3 theta plus minus 2 alone. At this step, you want to check and make sure you're doing it right by checking what is underneath the square root. I'm sorry, what is inside, sorry about that, inside the parentheses. And if those are the same, then we're on the right track here. And that means that that's going to be one of your factors. And then the other factor will be the 2 GCFs that we factored out, so the 4 theta plus 1. And so what we're going to get here is we're actually going to get 2 solutions. Okay. We're going to use the zero product property to solve for both of these, and we end up getting theta equals 2/3, and we get theta equals negative 1/4. So let's go ahead and we'll plug these back into whichever one seems simpler to do. I guess maybe the second one might be a little easier to deal with, or we'll have to find common denominators there. So actually, I'm going to double back here and say let's go ahead and plug it into the first one. Let me scroll down here just so we have a little bit more room to work. Okay, so for each one of these, we need to find a corresponding R value. Okay, so when theta is, let me just scroll down, just give me a little bit more room here. When theta is 2/3, we'll plug that in here. We'll get 12 times 2/3 squared. Okay, that's going to be R. And we'll do the exact same thing for negative 1/4. So 12 times negative 1/4 squared. And we're going to throw that in the calculator. Okay, no need to do that by hand here. So I'm going to pull up my trusty calculator. And let's go ahead and compute this. Yeah, so we got 12 times 2/3 squared. So we get 16/3. Okay, so that's one of them. And then the other one would be 12 times negative 1/4. Let's make it a fraction so it'll spit out a fraction for me. And that should be 3/4. Okay, so we get 2 coordinates here. We get 2/3 as, oops, it should be r comma theta, my bad. So you should get 16/3 comma 2/3. And the other one, the other intersection, the true intersection, is going to be r is, what did I say it was? Let me take a look. 3/4 comma, remember it's r comma theta, negative 1/4. Okay, so let's take a look at number 4. Okay, let's box our answer here. We got our 2 solutions. These are 2 coordinates that are going to satisfy both of these polar equations. Let's try to solve the second one here, number 4. Now, this one's going to be a little bit easier because, well, at least the first part will be, because one of the functions is just r equals 2. Let me get this calculator out of the way. Get out. All right. All right, so we've got r equals 2. And so that's just going to be a circle with a radius of 2. And then we've got r equals 1 plus 2 sine theta. And it says find the xy point where the two curves intersect. So actually what we want to do here is we want to identify the polar coordinate first, and then we'll convert that polar coordinate into rectangular coordinates. So we'll do basically what we did over here. We won't have to do all the factoring or anything because this will just be basically like a linear equation. And then, oh, actually, no, it won't be linear. We'll have to solve a sinusoidal equation. Not a big deal. We can still do that. But let's just get started here. So let's set the equations equal to each other. So get 2, or here, I'll put this one on the right, left-hand side. 1 plus 2 sine theta. Theta is always kind of a pain to get, so I'm going to copy that so I don't have to type it every single time. Equals 2. And then we're going to subtract 1 from both sides to give us 2 sine theta equals 1. We'll divide both sides by 2, and that'll give me sine theta equals 1/2. All right, so now we'll go ahead and find on the unit circle, what theta values will work here. So I'm going to bring up my trusty old unit circle, find where is sine equal to 1/2, and I see that sine is equal to 1/2. We're looking for the y coordinates, recall, at pi over 6 and 5 pi over 6. So my theta values that will satisfy this are going to be theta equals pi over 6 and 5 pi over 6. Now, just like with the last one, I am going to have to find the r value for both of these, but it will be super easy because we already know what it is. It's explicitly given in the problem. Let me replace these pi's. I really like how Desmos will just know that I'm trying to type pi. Cami needs to get his game together. Come on, Cami. All right, there we go. Okay, so we know what the theta values are, and we know what r is for both of them. It's going to be 2 no matter what. So our coordinates here in polar form are going to be 2 comma pi over 6. Oh, let me just go ahead and copy it from down here. 2 comma pi over 6 and 2 comma 5 pi over 6. And those, if my question was, where are the coordinates in polar form, where the two curves intersect, it would be right here. But it's asking for the xy coordinate. So we need to convert that. Let me get rid of that unit circle so you can see everything I'm typing over here. So yeah, again, we've got our two coordinates in polar form, 2 comma pi over 6 and 2 comma 5 pi over 6. But we need to convert this to xy, and we're going to use those same conversions equations that we used before. So x equals r cosine theta and x equals r sine theta. So x equals r cosine theta. Let me just, I guess I can just copy them from above, these fancy little equations. Put those over here, and I'll kind of separate these out because I want to calculate these separately. And actually, I'm going to have to do it for both of these. Right? These are two separate points, so I'm going to need actually another set here. So one way that you can kind of think of these is, since we know it's going to be a coordinate, is we can actually just write it as a coordinate and just say, okay, well, that's my x, right? And then my y will be the r sine theta. So I can write it actually like this. Check that out. Okay, we're in business now. All right, so we need to compute the x and y coordinates for these 2 points. I'm just going to delete all this stuff. We don't need any of this because I'm gonna use this format since we're gonna be ending up with a point anyway. Oh, nope, didn't like that. Nope. Come on, Cami. There we go. All right, so so we'll start with this first point, right? 2 comma pi over 6, where the r is 2 and the theta is pi over 6. So we're going to type that in. Be 2 times cosine of pi over 6. Okay, Cami, just work with me here. Come on. There we go. I'm going to just copy that over because I'm going to have to type it a bunch of times. Okay, so cosine of pi over 6, and then my y-coordinate will be 2 times sine of pi over 6. And I'm going to evaluate those using the unit circle. So I'm going to actually bring my unit circle back just for this. I'm going to move it over a little bit, though, so it's not blocking all my work. Get out of there, calculator. We don't need you right now. Actually, can I fit that? I think that'll work. Okay, so yeah, cosine of pi over 6 is going to be root 3 over 2, and sine of pi over 6 is 1/2. So I can now simplify this and say this is 2. Oh, okay, well, whatever. 2 times the square root of 3 over 2. Doesn't look like my square root notation either. No problem. I'll get this right one day. So square root of 3 over 2. And this should be times, so I'll just throw a little dot in there. Do we have a dot? I don't know if I have a dot here that I can use. So just know that this is times. I don't really see a dot there. I guess I could draw one in. Dink. Okay, so 2 times root 3 over 2. And then my y-coordinate is going to be 2 times 1/2. Okay, so really what we end up here with is, I'll just highlight all this, is we end up with square root of 3. Can you all see that? Yeah, I think we're still good on spacing here. So we get square root of 3. Don't need this anymore, comma 1. Okay, so there's one intersection, xy intersection. Over here, we're going to do basically the same thing here, except instead of using pi over 6, we're going to use 5 pi over 6. So I'm just going to copy and paste that. So we got 5 pi over 6 on both of these. So at 5 pi over 6, take a quick look at that unit circle. And we've got negative root 3 over 2, comma 1/2. So it's going to be very similar here, except we're going to have negative root 3 over 2. And then still positive 1/2. Draw a little multiplication here so you don't think that's a mixed fraction. Okay, 2 times. Okay, there we go. All right, so now we're going to multiply that out, and we're going to get a very similar point here. We are going to get negative root 3, comma 1. So those are my 2 intersection points. Now let's look in Desmos and see, let's double check this. I'm pretty sure we're good, but it doesn't hurt to double check our work here. So I'm going to go over to Desmos. I'm going to plot these out. So let's get rid of that unit circle. The first equation is going to be r, I don't know if you can really see this, but r equals 2. It's going to look like that. It's this red circle. Okay, it's a circle with radius 2. I guess I can zoom in a little bit so you can see it a little nicer. And then, there we go. The next equation I'm going to graph is the 1 plus 2 sine theta, which is, oh, okay, all right, we get a nice little design like that. Looking like one of those spirograph things. And then you can see we have 2 intersection points, right? We got here and here. So if I plot root 3 comma 1, that's going to be right there, and negative root 3 over 1 is going to be right there. So we can say, okay, yep, we're good. Now, if you're trying to use Desmos to check this, make sure that your coordinates are in rectangular form. What I mean by that is, like, if I go back to this problem number 3 over here, plotting these points, like if I'm going to check these equations in Desmos against these coordinates, you're not going to see that they intersect because these coordinates are in polar form. And unless you, I just personally don't know how to put that into rectangular, put that in polar form into Desmos. So you would have to convert this to rectangular form first and then input that into Desmos. It's kind of weird because it will take the polar equations, but it doesn't seem to like the polar points. I got to do a little digging, figure out how exactly to plot those out. But if you were to convert these to rectangular form, you could check that in the same way. So everything looks good here. I'm pretty confident we got it right. So that's how you find intersection points between two curves. Remember, you can either find them in polar form or you could find them in rectangular form. Although to find them in rectangular form, like this one over here, you do have to find them in polar form first, and then you just convert the coordinates. All right, let's take a look at number 5. A polar curve r equals 2 theta plus sine theta is defined on a domain from 0 to pi. There's exactly one point P whose x-coordinate is -4. Find the y-coordinate of the point. So basically we've got a polar curve, and we know that there's going to be a point on that curve where the x-coordinate is -4, and we're trying to find the y-coordinate of that point. Okay, so let's break this down. First of all, we know that the x-coordinate is -4. So I'm going to write that down. So x equals -4. Now, the tricky part here is we've got a function that's in polar form. So what we need to do is we are going to convert this statement to polar form and use it to find the y-coordinate. And I'll show you how that works. So let's convert this to polar form first. And that is x is equivalent to r cosine theta. Oops. Wait, what's going on here? There we go. Get that theta in there. Okay, so r cosine theta is -4. And if we solve that for r, we're going to get r equals -4 over cosine theta. And why are we doing this? Well, we're doing this because we want to figure out what is the y-coordinate when x is -4. And so we've converted this to a polar form. So basically we're going to have a our curve that we're interested in, right, the 2 theta plus sine theta. And we're also going to have another curve, which is just that vertical line where x is -4. And we're going to use this, and we're going to use the calculator to find the point of intersection between these two curves. And that should give us our value. So here's the problem though. If I try to solve this like I did the previous problems, what I'm going to end up with is this equation, -4 over cosine theta equals 2 theta plus sine theta. And this is not something that we're going to be able to solve algebraically. Not yet, at least. Not until, well, not in precalculus at all. Okay, so don't worry if you're like, I don't know really where to go with this algebraically. That's totally fine. Let's make this a little bigger. So we got to solve this with the calculator, and that's why I have a little calculator symbol over here, because we are going to basically set up a system of equations and find the point of intersection in the calculator. Okay, so I'm going to simplify this just to make it a little easier to work with, and that is I'm going to rearrange this so that 4, or -4, is equal to 2 theta plus sine theta times cosine theta. So basically I'm just multiplying that cosine theta to both sides just to make this a little simpler. Okay, now how do we use the calculator to actually solve this out? Let's bring up the calculator. So in the calculator, this is going to be kind of weird, but we're actually going to be in function mode. So in mode, we're in function mode right now. There is a polar mode, but when you're in polar mode, and we can take a quick little look-see here. If we're in polar mode, and let's say I plug in the two equations that I'm interested in here, 2 theta plus sine theta, and -4 over cosine theta, which we know is going to be that vertical line. We take a look at the graph. Okay, so there is the first function that we're interested in, and then so we see we got two intersections here, right? So this is that vertical line x equals -4. But the problem here is that we can't use the intersect function like we can in function mode. So like if I go to second calc, there's no intersection function here. It's just sort of missing. So what we have to do instead is we're going to go to function mode. And we're going to type in the two equations and just use x to represent theta here. So I'm going to type in -4 as my first equation. Okay. And then for my second equation, I'm going to have 2 theta plus sine theta. And I know it's saying x, but oh, and you know what? I'm going to need parentheses over here. Times cosine theta. Hit graph. Now this is not going to be what the graph like is supposed to look like in terms of like this is not what I'm doing here is I'm just utilizing the y equals the function mode here so that I can locate where those intersections should be. Now we see we have a lot of intersections here, right? And if we were to go back to polar mode, the reason why we're not seeing so many intersections on here that we would kind of expect is because we're only seeing part of the graph here. We're not seeing the whole thing. If I zoom out, see the spiral is going to continue, but we're still not seeing it all, and that's because we're only seeing theta go from 0 to 2 pi instead of just all numbers. So if I do like -100 to 100, I don't know how quickly this is going to actually graph. It might take a while, but yeah, that's maybe too much. This is taking too long. So let's back that up a little bit. Don't want to overwhelm the poor little calculator. So let's do like -10 to 10 maybe. See if we get a better picture here. Okay. So you're going to see there's many more points of intersection here, right? Okay. Boom, boom, boom. We got a bunch more. And if you could see, if we were to extend this further, you'd get even more. So that's why when we look at the graph, we're in function mode, why we're seeing so many more intersections. And so what we're going to do here is we're actually going to restrict the domain. Let's see, let's go. Are we in function mode? Yes, we are. We're going to restrict the domain to be what it says, which is, let's move this out of the way. It's defined on, oh, it's already over here, 0 to pi. So we're only concerned with the intersections between 0 and pi. So, oh, that looks kind of cool. Let me go back there. Huh? Check out that graph. This might be cool to throw into Desmos just to see what kind of detail we get. Anyway, I won't waste your time with that. Let's zoom in back to where we are interested in. We're really only looking from 0 to pi. So pi being like 3.14 is going to be like right here. So we're really just looking between here and here. Looks like there might only be one intersection in that interval. So I'm going to change my window to go from 0 to pi, just so that that's all I see. Okay, so there's the -4, right? And the rest of that, we're looking for that intersection. It's going to hit right here. Okay, now what you got to remember here is like, what are these variables actually representing? In this case, x is not x. X here is theta, and y is not y. Y is actually r. Okay, so we're interested in the theta coordinate here. And that's what we're going to do. So, so let's hit second calc. We're going to do intersect, and we could just really hit enter, 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 and there we go. Okay, so what this gives us is our theta value, 2.39. Okay, so that's our theta. In fact, I'm going to go over back to our little notes here and say, okay, well, theta in this case is approximately 2.392. We'll go 3 decimal places there. All right, so we know what theta is. Now let's hop on back to polar mode, since that's going to give us a better picture of what the graph actually looks like. And I do want to fix this window. I want to go from 0 to pi just so I don't see any extra intersections here. Oh, let's fix this. Let's go back to -10, 10 on the x. We just want theta to be from 0 to pi. So we're going to look at the graph, not the table. There we go. So really, we're looking at it for this point right here. And it should make sense that theta is about 2.3. It's given to us in radians. A radian is roughly 60 degrees. So 2 radians would be roughly 120 plus an extra 1/3 of a radian. So now we're talking about like 140 something like that degrees. We could convert it if we need to. But yeah, does this look like 140 degrees-ish? Yeah, kind of. Okay, so this line right here. If this was our terminal side, and this point is right there on the terminal side, then yeah, that would be like 100 and something, maybe 50 degrees. So anyway, we've got our theta in terms of radians, and we can use that to calculate the y-coordinate, okay? Because we don't need the calculator, well, I guess we will need the calculator to actually multiply this out, but if we know where theta is, we can calculate y, because how do we calculate y? We do y equals r sine theta. Well, now that we know r, right, and we know theta, we should be good to go. Actually, you know what? I take that back. We don't really know r. We are going to have to do this in the calculator, okay? Because where is r? We don't really know how far away this point is from the origin. I guess we could figure it out, but there's an easier way to do this, and that is we want to just trace to that theta value. So in the calculator, we're going to hit trace, and we're just going to trace to when theta is 2.392. And it gives us that point. Look at that. Okay, so it gives us the x and the y. It is approximate, so we thought the x was -4. It should be, but there is a little bit of an error here because we rounded. So this is close enough, though. And so we get our y value is 3.724, I guess. So the y value. So we can get rid of this statement. We don't really need this statement. I do want to put a few more notes on here, just so that when you look back at here, you kind of remember the steps on how we got there. Let's change this to approximately, because we don't know, it's not exact, 3.724. So there we go. That's our answer there. But just to clarify here, a couple things. So the first thing we did was, let me just hide this calculator and get this out of the way for a minute. First thing we did was we rearranged the x-coordinate equation. I'm sorry, we didn't rearrange it. We converted it to polar form. So let's see. Convert known coordinate equation to polar form. That's going to be your first step. And solve for r. Okay, so that's step one. That's what we're doing over here. Okay, let me just kind of highlight this real quick. Okay, step two is we set the two r equations equal to each other. So set two r equations equal to each other. Now, we didn't really have to do this next step where I moved the cosine theta over. That's not required, but I think it's easier to see the lines if you've got just a constant on one side. So you're welcome to leave it like this, but I think it's easier if you try to get a constant. Okay, so that was the second thing we did, and then after that we put both of those equations into y equals. Okay, so plug both sides of the equation into y1 and y2. All right, so that was what we did, and then to find this theta value, what we did was we did second trace to get to the calc menu, and then we select the intersection function, and then I think I just hit enter, enter, enter. Okay. The y value, or I'm sorry, the x value is actually theta. It doesn't really like that theta in this text box, so I'm just going to leave it like that. Okay, so that's going to give us theta. That's where the theta comes from. Okay, so, and that's kind of explaining where this guy comes from. So once you have the theta, then you can go back to polar mode. Okay, so right now we're in function mode. Okay, so just, I know these are like notes on notes on notes, but we're in function mode. Let me scroll down a little bit. And finally, to get to your answer, you're going to go back to polar mode. So you're going to enter both equations, both polar equations, into polar mode. And that's going to be like an R1 and R2. Press the trace button and then enter the value you got for theta. And that's it. It will give you the y value after that. So if you're trying to work a similar problem to this, just follow these steps and you'll be good to go. Can you see this okay? To each. Yeah, you can't see the each. Let me try to bring this over just a tad, see if that can help. There you go. Okay, so there you go. Whew, that was a tough one. There's a lot going on with the calculator on this particular problem. So that's how you're going to work out a problem like this. It's really just more about knowing and understanding how to use the calculator correctly, and then you should be okay. Number 6 here, I've got one last problem for you. This is another calculator problem. Find the theta coordinate of the point of intersection. And we're going to assume radians here. And really, in general, you should always be assuming radians. So to do this, we're gonna take a similar approach to the problem that we just solved. So basically, go to function mode. And like we did in the previous problem. Okay, so in function mode, let me pull that up. Let's make sure I'm in the right mode here. Mode, I want to go to function instead of polar. And I want to type in both of these equations. Okay, I know it's going to say x, and we really like it to say theta, but it'll work. Okay, so doing sine x, just, wow, I can't talk today. To do sine squared theta, you have to put the squared on the outside, just the way the calculator's set up. So just be aware of that. And then the second equation is just theta. All right. So we're going to look for the intersection point in between pi over 2 and pi. So let's change our window to go from pi over 2 to pi, so that we're not seeing any other potential intersections that occur. And I'm going to look at the graph, and it looks like there's 3 sine squared theta, and there's the other one. So we're looking for this intersection right here. We're going to get theta right away. So I'm going to hit second calc, go down to intersect, enter, 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 and there you go. Okay, now remember, the x is really theta here. So theta is going to equal approximately 2.137. And so that's it. We could find r, but r equals theta, right? So r is known right away. Okay, so that was pretty easy. There's, we did basically the same thing we did before, but we didn't have to go through all those other steps. So the follow-up question is, when is it greater than theta in the interval above? Okay, so when is that first function, and just to clarify here, the first function let's make this a little darker so you can see it a little better. You just hit enter on that. So you see the dark function. We want to know when is that above the other function on this interval. And it looks like it's going to be above the function before we hit that theta. Okay, so it's going to be from pi over 2 to that theta value, which is 2.137. All right. I just realized I don't know if you saw everything I just did in the calculator, so let me show you again. Maybe you did. I'll have to review the tape. But welcome. All right, sorry about that. I had a little interruption there. So we're looking at the calculator, and I'm going to have 3 sine theta squared. This is how we're going to notate the sine squared theta, like we have above. You just can't put the squared into the calculator right there. So this is just the syntax that you use to make that work. And then we have r equals theta. I know we're in function mode, but that's just kind of how this works, because like in the last problem, you can't find those points of intersection in polar mode, unfortunately. So we're going to hit second trace, go down to intersect. Now I've already fixed the window here. Let me just show you real quick. These decimals probably don't mean anything to you, but this is pi over 2 to pi. So I'm just using the domain that's given. So I'm going to go to second calc, go down to intersect, hit enter, 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 and this is where I'm getting the 2.137. Remember, this is not really x, this is really theta. So the theta that we're interested in is right here. Okay. Now, going back to this follow-up question, when is the 3 sine squared theta greater than theta? So if I go to y equals, what I did was I made this first equation a little bit more bold so that you could just tell which one's which. And then when I go to graph, I can see that that bold equation is above the other equation from the beginning, from this pi over 2 line, all the way to that point of intersection. And then when they cross over, theta actually goes above. So the way that we're going to write the solution here, when is the first equation above the second equation, is we're going to write it in interval form. So I'll write it like this. Let's see. So we've got theta. Oh, I didn't like my theta there. Let's try again. There we go. Is an element of okay, this set. We got pi over 2 comma 2.317. All right. And that's it. And the reason why we don't want to actually include this is because they're actually equal there. So that this function is not greater than theta at this point, but it is at pi over 2 at the beginning. So that's going to be your solution there. Let's make that look a little cleaner. And that's pretty much it for today. So let me know if you guys need any help, and have a great day.